Okay, today I'm going to start a new topic, and it is also the last topic of this semester. The topic is how can we solve the ordinary differential equation? And for a lot of engineering problems, and we establish a model to describe the problem, and also we like to solve the model to get the estimated results of the concerned problems. And the model, a lot of time, the model will be the differential equations. Since a lot of engineering problems, we have the intended target function, and also we have some parameters. And the target function, the relationship between the target function and the related parameter, it will lead to the rate of the change between the target function and the concerned parameters. For this kind of the problems, usually it will lead to the differential equations. Okay, and for the structural analysis problems, there are also a lot of questions. They are related to the differential equation problems. And later I will give you an example problems. I like to ask all of you to finish a term project related to this topic. Okay. And today I'm going to talk about the first order differential equations. Let me see. Okay, let's say the u is the target functions, and the prime means the first derivative of the u functions, and the u prime you can say which is the okay. Let's say for different steps, let me erase the time parameters. Okay, the first derivative of the u to the du to dx is equal to the f of x, and usually the f of x is a known functions, but for some special case, the f of x is not a continuous function. Probably we know the f of x only at some discrete points, but it is not a continuous function. Okay, so that's only the first order differential equation. But a lot of problems, they are related not only to the first order differential. Sometimes we need to consider the second derivatives, the third derivative, or even the fourth derivative of the target function to the parameter concerned. Okay, but we can solve the problems step by step. For example, if we consider a problem which is the okay, for example, if we consider a second derivative of the u to the x, or you can say u double prime is equal to g of x. Okay, for a problem like this one, you can consider take the Okay, then you can say the u double prime is equal to g of x. You can change the basic unknown functions u to be the u. If we take the u prime as the basic unknown function, then it will be the u prime take a first derivative which is equal to the g of x. Then it will be changed to the first order differential equations. Okay, so even we consider only the first derivative, however, if you like to consider the second derivative or third derivative, you need to take 2 or 3 steps to solve the problems. Then you can still get the results. Okay, so today we are going to consider only the first order differential equations. Okay, let's say that's the differential equations considered for the Okay, let's consider the domain of the x. Let's say it is between the alpha and the beta. Between this, for the domain of the x, between the alpha to the beta, we need to satisfy the boundary conditions. And sometimes we have the Okay, sometimes we know the solutions at the beginning, and for this type of problem, it is the boundary condition problems. It is the boundary conditions, and sometimes we know the u of beta. Okay, we have either one. Usually we know only one of these. Either we know the u of x equal to alpha, or we know u of x equal to beta. Usually we know only at one end we know the solution, the solution function u. The function of the u at the left end, or the function of the u at the right end. Usually we know only one of these. Okay, so we have the boundary conditions, we have the control differential equations, and we like to solve the u of x function. Okay, we like to find we like to get the u of x functions, and the u of x, the requirement for the u of x functions. First, it needs to satisfy the control differential equations. Also, the u of x functions can satisfy the required boundary conditions. Okay, so if we can find such kind of u of x functions, then these functions is called the solution of the problems. So these functions is the solution of the problems. Okay, so that's the purpose. When we solve the problems, we like to get the solution of this one. If it is possible, it is best to get the continuous u of x functions. But right now we are not trying to solve the continuous u of x functions. Today's technique, we can get the discrete points of the discrete solution for the u of x. So we know the u of x equal to alpha, and we know the u of x equal to alpha plus delta x1 u. So sometimes we know, if we know a lot of the u value at different at the different locations, then it is although it is not a continuous function, however, you can say we can describe the change of the values of the u function. Okay, so take the screenshot. I will. Okay, so right now, okay, how can we get some discrete points of u of x? And let's say we can okay. First, we can divide the considered domain into m equally spaced interval. So that's the length of the interval. The delta x can be calculated by this formula: the beta minus alpha divided by m. And the n plus, we can get okay. So the first discrete point, which is called the x1. The x1 will be the left end point. The x1 is equal to the alpha. And the next discrete point will be the alpha plus delta x. And also we can calculate the x3 until the last point, the xn plus 1, which is the alpha plus n times delta x. It is the beta. Okay, so right now we are not going to solve the continuous u of x function. But right now we can, however, we can solve n plus 1 discrete points, and we like to get the estimated value of the u of x. Okay, so print the screen. Okay. the change of the function value will be the integration of the f of x from xk to xk plus 1. Okay, so for any interval, the change of the u will be equal to since the f of x is the differentiation of the u functions. And so if we integrate the f of x, then we can get the change of the u values for this interval. Okay, so that's the basic formula. And but sometimes the f of x functions could be very complicated functions, and sometimes the f of x, it is also functions of the x, or sometimes it is even functions of the u, and in this case it is called the nonlinear problems. If the f of x is a known functions, but for these known functions, it does not contain the solution variable, the u of x in the functions, then it is called linear problems. Okay, no matter which it is a linear function or nonlinear functions, the techniques introduced here can be used to solve either nonlinear or linear functions. Okay, for this one, and we will try to use okay, the first technique, we will use a constant to replace the variable functions f of x. And how can we use the constant? We will try to use the f of xk, the functions of the f, the function value of the f at the initial point for this interval. Okay, so if we use this one to replace the original function f of x, then however you can say it is a you need to add an approximate sign, since the real f of x functions, it could be different from xk to xk plus 1, and also the f of x could be related not only to the location x, also it could be related to the intended functions u of x also. So however, if we use a constant, although this constant which is the function value at one of the endpoints for the f of x, however, it is only an approximation. If we use these approximations, then okay, so it is the in this way, we can solve the u of xk plus 1. We can solve the u of xk plus 1. Okay, so, however, we need to know the f of xk. Okay, take the screenshot. Okay. Okay, usually we start from usually we will start the solution procedure with the point with the known boundary conditions. So if we know let's say we know the function value u of x equal to alpha, let's say, which is the u alpha. So that's the given boundary conditions. However, we assume right now the boundary conditions which is at the left end. So then we can calculate the u of x. Okay, so that's the u of x1, u of x2. Since we assume the alpha is the x1, then we can solve the second interval point, the u of x2, the x2 which is equal to the alpha plus delta x, and the function value of u of x alpha plus delta x is equal to the u alpha plus the slope at the end point x equal to alpha times delta x. Okay, so we can solve the u of x2. Then we can solve the u of x3. Okay, then we need to use the function u of f of x equal to x2 times delta x to get the plus the solve the u of x2 to get the u of x3. Then we can continue this procedure until the u of xn plus 1, u of x equal to beta. Okay, so in this way we can solve all the u function values at the discrete point. For this method, it is called the Euler's method. Okay, so this method is called the Euler's method. Okay, take a screenshot. Okay, also we can use some other methods. And in this case, so the Runge-Kutta method is the second order. Or you can say it is the second order, the Runge-Kutta's method. For this method, we will use the slope at both ends. So for dx. Okay, so okay, so if we there. Okay, sometimes the f functions is not only related to the x. Sometimes the f functions also related to the solve the the value of the u. Okay, so so in this way we can take the slope at the end point, the left end point, and the slope at the right end point, and then we calculate the average of these two to get the approximate f of x functions. Okay, so print the screen. Okay. Okay, sometimes the f, which is the f of x and the u, the f function is not only related to the parameter x, the function value is also related to the solve function of the u. In this case, it is the nonlinear problems. Okay, if we consider a nonlinear problem, then the slope f, which is not only related to the x, also it is related to the u values. Then we will estimate okay, then we need to estimate the u functions at the right end. and you will say that's the first estimation. Okay, first we need to estimate the approximate function value at the right end. We can use a function like this one to estimate the function value u bar. Then we can calculate the beta. Okay, first we use the slope at the left end. We can use the Euler's method to estimate the function value at the right end. After we get the estimated value of u bar, then we can calculate the slope at the right end. After we calculate the slope at the right end, then we can follow the second order Runge-Kutta method. We can take the average of the f function, the function value at the left end and at the right end, and then the average of these two to calculate a more accurate ux plus 1. Okay, take it spring. Okay, so so far I introduced two different methods. The first method is the Euler's method. The second method is the second order Runge-Kutta method. And I'm going to give you problems, and you need to solve these problems as your term project. And I will separate it into 2 weeks, 2 weeks homework, and after 2 weeks you need to write your report for the term project, and you need to turn in them before the end of this semester. So in the final exam week, you need to turn in the term project. Okay, so what is the problems? The problem for the term project, it is the cantilever beam and subjected to the distributed loadings. The W. Okay. And the moment of inertia, you need to calculate it by yourself. It is a rectangular cross section. The depth of the section is the 60 centimeters, and the width of the section is the 40 centimeters. So the E value, you should know the E value. It is for the concrete, for the steel. It is the steel section, and let's say, let me change the Okay, let me change the formula. 15,000 times square root of 280. That's the E values for the concrete strength with the 280. Okay, we know the E and I and the L. What is the L? L is equal to 5 meters. And the W, which is equal to 5 tons per meter. Okay, so at the right end, we have the maximum distributed load and the value of the W, which is the 5 tons per meter. At the left end, also which is the supported by the fixed end. At the fixed end, the distributed value, which is equal to 0. It is a linear shape. So the W is changed from the 0 to the maximum W. Okay, so for this one, that's the problems. Okay, so that's the problem we like to solve. Okay. Let's assume okay, let's assume the V of X, and usually I assume the positive V value, which is upward displacement, and the V of X, which is the displacement functions from the left to the right. So the V of X, that's the solution functions we like to get for these problems. Okay, and also we know the theta of X. That's the rotation of the center line, and we can calculate the rotation for the deformed shape at the different points. That's the theta of X, and also we can calculate the curvature of the X. Okay, I believe all of you learned it from the mechanics of the material. And if we take the derivative of the theta, then we can get the curvature at the different locations. And it is called the kappa of X. And if we know the curvature of the X, then if we consider the flexural deformation and if we use the mechanics of material, then we know the EI times kappa, which is related to the M of X. The M of X, which is the bending moment at the cross section. Bending moment at the cross section. And also we know the if we take the first derivative of the bending moment, then we can get the shear force. And if we take the derivative to the shear force, then we can get the distributed loading. However, we need to add a negative sign, which is the negative W. Okay, so that's the formula. If we combine all these formula, then you can get EI times the fourth derivative of the V functions, which it is equal to the negative W. Okay, so it is the control differential equations. It is a fourth order differential equation, since the highest derivative which is equal to the 4. Okay, so that's the controlling differential equations. And let's take a break, and I will continue to discuss about the boundary conditions of these problems in the next hour.
对，那625呢？